So, and one of the things that I can mention here with this one is that part of the reason I do this is because, of course, I know what my course is doing. Realistically, we are a 5 credit hour course. I know that we are one of the most brutal courses that you end up taking. I know it is an extremely stressful course. I'm aware of the circumstance, is the best I can say with that one right now. We've got a lot of material to cover, and it's my job to make sure that you get as much of it as you possibly can, and then to take some measure of how much you do get it. So I understand that I do have a lot of role in that stress that you guys feel and all of those details surrounding things like that. One of the details that I do like to highlight, though, is why you're here in the first place. Why you are in this course in the first place is because there is something in science that is interesting you, that is bringing you here, that even if you don't want to take this course specifically, there's a reason that you're taking this course and there's a reason that you're learning this material. And one of the biggest things that I imagine is that it is very, very easy to lose sight of what got you inspired in the first place. And when you lose sight of what got you inspired in the first place and you start to face that burnout, it's not fun. And I know that very well because not long ago at all, I was a student, right? This is only my second year of teaching. And before that, I was a student right up until then. So I have been through all of that, been in the trenches along with you guys. I'm on the other side of the trenches at this point, but I know what it's like to be in them. And so this is hopefully just kind of my, kind of let's stir that up a little bit. Let's remind ourselves what out there is very cool, what's out there very interesting that we can talk about, that we can re-inspire ourselves. And then one of the other things that I like to do with this is kind of a more subtle effect, but I like to kind of talk about some of these things to explore what's out there that you guys can be doing as well. That's a little bit more difficult right now because, of course, we're not very well in person. But as we are moving back to in-person courses, because we're supposed to be back fully on campus in the fall, if any of this stuff has sounded interesting, I would highly, highly, highly recommend, please go get involved with research. So many of your professors are doing different types of research, and it doesn't even have to necessarily be in your department. Look around, see what other people are doing in their research, see if you can work with them, see if there's something you can contribute, because many of the professors here, they don't require any sort of expertise of you before coming in, right? There's always a job to be done. There's always some hands-on experience you can be getting with a lot of these different research labs. And sometimes you find a new passion through that. Sometimes you find something fantastic that you are already passionate about, and somebody is working on that, and you can get some hands-on experience. But I really, really, really can't recommend enough. Please, please, please get involved with the research going on here. Do some of this science. Don't just be taking these things in classes and look at this and thinking that's all there is. Try this stuff out for yourselves. I really can't recommend that enough. I got involved with the research my freshman semester. Or my freshman year. It was my very, very first semester. I was asking my physics 181 professor at the time what kind of research he did. And I got involved in that research lab immediately and I carried that all the way through my master's. I stayed within that lab for 6 years. I found a lot of passion in there, and I shifted a lot of my focus. I really realized what a lot of my passions were when I was doing that kind of research. So that's all kind of a lot of what this is about, kind of get you aware of science, thinking beyond just the course material. Why are you learning all this stuff in the first place? I have a pretty strong feeling you're probably not just studying buzzing strings the entire time. But, some of that stuff can help you understand why we learn this stuff in the first place, where we can benefit from all of this knowledge that we have here. So I bring that up. Please do think about it, especially as we move into next school year. That's a fantastic time to get involved. A lot of people are going to be very, very active in their research, and they would be more than happy to have you helping out, however they've got a spot. So let's go ahead and talk about some of this material, though, right? I think we've kind of beaten around enough without actually getting into our stuff for the day. So a little bit of context on this one. Wiggle, damn it. Man. Sometimes he wiggles, sometimes he doesn't want to. wave motion. Right, and this might sound a lot like at first, hey, wait a minute, isn't this chapter 16? Or just kidding, isn't this just chapter 15 all over again? And I'm here to say, kind of, but not really. There's some pretty distinct differences here. What do I mean by wave motion? I mean, well, let's imagine a really bad example to start. And I think this is a fantastic way to imagine this. Take our vertical spring. Right? You got the vertical spring in mind, so you've got the vertical spring, you've got the block on top, and it oscillates back and forth. Now imagine you just slide that thing across the floor while it's oscillating. Can we agree that the oscillator probably still reacts pretty well with everything that we have been doing so far? Right? What has changed? What has actually changed between this thing moving and this thing being still, all of our chapter 15 stuff? Not really a lot, but there will be a few differences. And I wanted to start with that bad example because it's not something that we'll ever talk about in that same way, but there are other types of oscillations that you can have that you have probably experienced long before you came to this class. Take a pebble, drop it into a pond. What do you see? You see waves propagating outward. That is another example of an oscillation, but an oscillation that does not take place in one fixed location anymore. Now that oscillation is allowed to propagate and travel rather than just being in a fixed location. So that is what we're going to refer to as a wave. A wave is some sort of organized disturbance, and when I say organized disturbance, I mean sine waves, right, that travels through some medium, oftentimes but not always, at a well-defined speed. It's not the same thing as the medium itself, and not all of these waves will have mediums, but some of them do. In the case of the pebble dropped into the pond, the medium is the pond, the water. That's what's actually acting as the wave. When I'm talking like this, that's another example of a wave, right? But in that case, the medium is the air. It's why, despite the fact that Star Wars would have you believe otherwise, there's not sound in space because there's not a medium for the sound to travel through. On average, the density in space is about 1 atom per cubic meter, which is not very dense. That's not dense enough to actually propagate sound waves very efficiently. So it's not going to occur very often. But one of the interesting things about this one, anybody that has been in a wave pool or has gone to the ocean and felt like water waves hitting up against you, you probably know pretty well that, like particles, waves can carry with them energy and momentum. When you're in a wave pool, that wave hits you and it carries you. Right? And when you're in the ocean, you can feel some of those larger waves will kind of crash into you. They've got some momentum associated with them. They don't behave in the exact same way as particles, but they still have energy and momentum like regular particles would. So let's talk about a few different varieties here, and we're going to keep kind of expanding on this one. So 3 main big categories of waves, and then generally there are 2 types within those. Mechanical waves are probably what you are most familiar with. They are waves that are traveling through a medium. So sound waves, water waves, spring waves. If you whip a jump rope, if you whip a regular whip, all of those would be considered mechanical waves. So generally speaking, they're all traveling through some sort of medium, right? They've got a wave speed that is defined by that medium, oftentimes. And then finally, oscillations can be transverse or longitudinal, and that's my 2 types of waves. That's going to be one that we're going to get into just a little bit more later on. But a transverse wave is kind of looking something like this. If we have a spring and somebody takes that spring and sends kind of a shake down it, that's a transverse wave. You see that wave traveling like that. Longitudinal waves are a little bit different. We'll talk about those soon enough here, but not quite yet. Electromagnetic waves are another very, very, very common type of wave, right? Because you see them right now. That is quite literally light is electromagnetic waves. Light, radio, sunlight, what causes your sunburn, all of those things are examples of electromagnetic waves. All of them, they travel on their own. The electric field, the magnetic field is one of those things that doesn't necessarily require a medium to travel through. It is kind of its own medium in a sense. But that one's a little bit more interesting because the speed of light is technically a fixed value, but we'll dive into that a little bit more when we specify, what's going on with light, because light's kind of funky. So light is a weird one because not only does it fall into the electromagnetic waves category, it also kind of falls into the matter waves category, because depending on who's looking, sometimes light is acting like waves, sometimes light is acting like a particle. You have heard of this particle description before, I'm sure, called a photon. And other particles can behave just like these same types of matter waves. But we're going to mostly focus here for now on mechanical waves, and we'll introduce these other ones a little bit more as time goes on. But for now, let's focus on this, this second line that I've got, wave speed determined by the medium. So what I want to start with here is let's look at a very common example, a very easy one, a string. Let's imagine some sort of string, and what I'm going to do is I'm going to send a whip down it, right? Send some sort of wave down it, and this is what that wave might look like. I shake it, it travels all the way down, keeps doing that thing, fantastic. So that dotted red line is what we would consider the equilibrium position. I have made this string taut, and I have shaken it a little bit, and that's the wave as it travels down. The wave speed depends on two things. There's a derivation for this in the book. But the two things that it depends on are the tension in the string and then a value we call the linear mass density. Not friction. I know it's the same value for friction, but realistically there are only so many letters that we have to use. And we've already exhausted all of the regular standard Latin alphabet as well as much of the Greek alphabet to the point that we use all sorts of random symbols, right? One of my favorite symbols is H bar, which is quite literally just an H with a bar over top of it. That's one of the variables we use. We use all sorts of strange things sometimes. We've got two different versions of phi. You've seen phi like this versus phi like this. Yes, all sorts of nonsense, right? So the point of the matter is we're going to see some repeat values here, which is probably not anything super new to you guys. But some linear mass density is essentially just how dense is that string? How thick is the string? How much mass is in that string? So a lead wire is going to have a much higher linear mass density than a standard fishing wire, for example. A sailing rope, one of those really, really thick ropes that are used to dealing with intense weather and high winds, that's going to have a much higher linear mass density than something like a yo-yo string. It's just a measure of mass per length. Kilograms per meter is what that linear mass density is. Take the square root of those two values, divided, of course, you've got the wave speed. How fast does wave travel down that string? And those are the only two things it depends on. So, concept check here. Let's imagine we've got the same string in both cases, no change to the tension or anything else like that, and we see two different waves traveling down the string. Which one is faster? Take your pick. Which one do we think is actually going to be going faster here? One answers C, two answers A. Interesting. It's a little bit different from the lecture that I saw earlier today. Somebody give me a reasoning. What's going on? Why pick A? What do we see about A that seems like it would be moving faster? Okay. A little bit less amplitude for the string. So the less energy going up, more forward. I don't know if I necessarily agree with that one entirely. My idea here is that I would think that the further away the displacement is, the more energy that it's got. And I'm thinking about this, perhaps I've got a little bit of an advantage on this one, right? I play a stringed instrument. So what I know from this one is that the harder I pluck, the more energy I put into the string, generally, the louder it's going to be, the larger the amplitude. So arguably, the amplitude does have something to do with the energy, but I don't know that it has anything to do with the speed. Because again, We can even try this one. Why not? We're having some fun with it. Right, today's a little bit of an easier day. It's a little bit slower. If I have any sort of string or anything else, and one of the questions I know talked about the guitar string at 440 hertz, and that is not actually a guitar string. They're lying about that, but we do have a 110 hertz. Let me try two examples here. If I play one note, okay, now I'm going to put a little bit more energy into it. Same string, same tension, more amplitude, but if that velocity was changing, I think I would hear a difference. Beyond just the volume, something else about the sound would start to change between a quiet note and a loud note. And while a string like this is not exactly what we're looking at, the string motion on an instrument is quite different than the string that we're seeing right here. Or rather, it's a specific case of what we're seeing right here. But at the end of the day, the only two things that the velocity actually depends on are tension and linear mass density. So I expect both of these should have the exact same velocity. And what do I mean by the pitch of the sound depends on the speed? We will see that in just a little bit. Let me come back to that idea in just a little bit here. The amplitude doesn't have a major impact on the speed. I see those two velocity vectors at the exact same length. Would the displacement affect the tension? Now that's a great point. Realistically, yes. There is a ever so slight difference because of displacement that does indeed affect the tension slightly. However, the impact of that difference because of displacement is very, very, very minuscule. Very minuscule. And when we get a little bit into a few more slides from now, let me pull out the guitar again and we'll talk about that one more time. So the two strings are the same. They are the same string. Two pulses travel along the same stretched string. One after the other. So there might be a very, very slight difference in the displacement, but I would argue that it's minuscule enough. It's kind of like our simple pendulum idea of like, all right, as long as we're not taking this out to an extreme, as long as we're dealing with realistic strings and we're not doing anything super crazy, the difference of amplitude is not significant enough to really change anything going on. Everything will be pretty much exactly the same. So the velocities should be the same. So let's try something here. Let's imagine we've got a wave speed because we know the wave speed depends on the tension, the linear mass density of this. I'm not sure what's, if it's the same stretched string the entire time. That's implying that neither the tension nor the mass density are changing. There should not be any change because it's the same string in both cases. The same stretched string one after the other. So there's nothing in there that's changing about the string, is what we mean by that one. Yeah, nothing changed about the string. It's the same string, just one wave after the other, no difference between the two of them. So velocity should be the same. Let's try something where we are changing that tension though. Let's imagine the wave speed on a string as we have measured it to begin with is 150 meters per second when the tension is 75 newtons. Take the same string, tighten it up a little bit more, increase that tension. What tension do we need so that we get a speed of 180 meters per second instead? Take a few minutes, see if we can come up with a good number for this one. Mu is indeed kilograms per meter. And I guess one of the things that I would highlight when we're talking about a linear mass density, think about like a yo-yo, for example. Take a yo-yo, cut the string on the yo-yo. You've got the string in your hand. How heavy is that string? 20 grams? 30 grams? For a lot of these things, and that's a full meter. So when you're looking at a lot of these quantities for mu, most of the time, expect to see a very small number. Oftentimes, it'll be in grams per meter, or perhaps even something like milligrams per meter. Because most of the time, we're dealing with not super thick strings, right? We're dealing with generally pretty thin strings. But anyways, let's go ahead and check some of these numbers. And I'm just going to do this one right on here. Why not? So what we've got, a wave speed on a string is 150 meters per second. So let me call that V1 and the tension T1. That is to say V1 is equal to 150 meters per second. T1 is equal to 75 newtons. And I know right off the bat that if we're talking about that wave speed, I know the wave speed on a string, V1, would be equal to the square root of T1 divided by mu. We take the exact same string and we tighten it up so that our wave speed is now 180 meters per second. V2 would be equal square root T2 divided by mu. And we're looking for T2. What is T2? Now, I think the easiest way to go about this one, there's a couple different ways, I guess, that you could consider this. I haven't put a subscript on mu, though, because it's the same string in both cases. The string did not change. So if it's the same string, even if it's under a different tension, it's the same mass density. So then, I think one of the easiest ways to take this is let me take V2 divided by V1. Let's try that. V2 divided by V1 turns into this nasty thing, square root of T2 over mu divided by square root of T1 over mu. But really why I went through all that trouble is because now I can cancel out those mu's. I don't even have to solve out for that if I don't want to. And if you do, you're welcome to do that. That's totally fine. But now what I've got, square root of T2 divided by square root of T1. T2 is exactly what I'm looking for. Let me square both sides. Let me move T1 over. V2 squared divided by V1 squared times T1 is equal to T2. And at the end of the day, T2 should be equal to 108 newtons. How do we feel about that? All right. So, here's where things are a little bit more complicated. So this is how fast a wave moves, and that's fine. But let's look at this video one more time before I get into it. Look at that shake. Do we see that thing moving around? If we look at one spot, for example, one spot goes up and then comes back down, but then I can see the rest of the wave moving forward in time. And then one other spot has a different reaction to that. It goes through the same motion, but at a later time. So our complication here is the fact that now we have a dependence on two different variables rather than our classic kind of oscillation. And for the question, can you obtain density first and then calculate the second tension? Absolutely. I just kind of skipped over that step. Right, I decided, let me just cancel out mu before I actually dive into this. Let me just not even bother doing that extra calculation. What we're looking at here, it's a sine wave. Everything is sine waves. I've said that before. Everything in the universe is sine waves. So this is not surprising that it's a sine wave. But we have this issue where if you look at one particular point, if I look at one spot on the string, if I look at the 0.5 meter spot, I see that thing going up and down in simple harmonic motion, right? Sine waves. If I look at the full string and somebody is constantly shaking it at a constant rate, then so too there do I also see that the whole string is now in a sine wave. So what we're seeing here, for example, is this graph over on the right. So this graph that I'm talking about right here, this is somebody took a picture of the string. Somebody was shaking the string and somebody took a picture. The graph on the left is, imagine that we looked at this spot right here. Or better yet, let's do something that matches a little bit better. We're about to go up in amplitude. So let's imagine we picked this point right here. We're looking at this point right here, and we want to watch what this single point does. As the wave travels, I have done this in the wrong direction here, I think. I should have picked this one. As the wave travels, so that wave moves to the right, I see that one single point go up, and then down, and then up, and then down, and then up, and then down, and then up, and then down. So it's a strange spot. It's tricky because it looks like our next spot is supposed to be this down here, but remember that this thing is this whole graph is about to go this way a little bit. And if it goes that way a little bit, then we go just a little bit up, and then 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 we hit our peak, and then as the wave keeps moving to the right, we go a little bit more down, a little bit more down, a little bit more down, right? It's what's happening right here. This wave is traveling to the right. If I follow along with what's going on, let me even do a brighter color on this one so we can see that a little bit better. My spot right here goes up and then back down. The wave traveling to the right ends up with something like that. So what we're going to do now is we're not going to talk about this in terms of x of t anymore, right? X of t was for simple harmonic oscillators. We want to focus on what's going on in the entire wave now. And what's going on in the entire wave is we want to talk about this value called displacement, d, that not only depends on time, but also now depends on x. Because again, let me keep going back to this video because this is a fantastic video. Every single point along the spring here goes through the exact same motion. All of them go through two peaks. But they do so at different times. Depending on where they are at, the point out here has to wait its turn. It has to wait for this wave to get all the way up to it before it's allowed to move up and down. Whereas at the exact same time, way over here, that one instantly feels the two peaks. So we've got a slightly more complicated equation. We have to model this in a slightly different way, and let me break this down into two separate pieces first. So let's start by talking about some of these variables, just so we can make any real sense of what equation we're about to see down here. Top half of this graph here. Snapshot in time, describe a few different things about what's going on. So we look at this thing, we have taken a picture, this is what the string looks like at this moment in time with all these waves on it. We have a value that we call the wavelength. And the wavelength is what we talked about before. It is to go through a full oscillation, peak to peak, valley to valley, or start point to end point. One complete sine wave, an up and a down back to our initial position. So that's what we call the wavelength. How long is that full wave? The amplitude, something you have seen before. The period, something you have seen before. The frequency, something you have seen before. None of those values are new. They're not picking up any new definitions. Wavelength's a little bit new. Wave speed is how fast this wave is actually able to move, which we talked about in the previous couple slides here. When we put all of that stuff together, we get this crazy description of all these different variables that can tie in together. And you'll notice here at the very end, I've got two new ones, kind of. But the wave speed can be written one of two major ways. The way that I commonly like to do is this one right here. Wave speed is equal to lambda times the frequency, the wavelength times the frequency. Or if you look at the one right before that, lambda divided by time, that's a distance divided by time is equal to a velocity. That seems to make sense to me. And then frequency, just being the inverse of period, multiplied by that distance, same description right there. Omega divided by k is a little bit strange though. And at first you might look at that and you say, omega, k, my good friends from simple harmonic motion, and kind of. See, angular frequency is the same thing that we just saw before. Angular frequency, omega, no different. 2 pi times the frequency, right? Some radians per second value in here tells us how fast do we go through an oscillation. How fast do we go through an oscillation? Angular frequency. K now is what we call the wave number, and this is a pretty different thing from our spring constant. It might share some similarities at first, but it's pretty substantially different. The wave number is more to do with how the thing is going to be oscillating. See, if angular frequency is the angular version of frequency, wave number is like the angular version of wavelength. It's a little bit different, but it's like how many wavelengths can we shove onto a 2π? That's what that's trying to say in a sense. It's a little bit strange, and the units for this, you can either write this as 1 per meter or inverse meter, or you can write this as radians per meter. Again, I know I've talked about this before. Radians are one of those units that kind of come and go as they please. I'm not super concerned about it. As long as you know that the unit should either cancel out or be radians inside of these things, it's all fine. Radians are one of those units that sometimes we think about, sometimes we just kind of ignore. Technically, every single time you see a 2π, radians come with it. But that's beside the point right now. The wave number is going to be one of these other pieces that we plug in here for this nasty displacement equation. And it looks kind of similar to what we've already seen before. But the big difference is this minus omega t. This minus omega t is a little bit strange, but I promise when we go through the derivation, it does intend to mean this value. What's going on, though, is that the wave is moving to the right. As the wave is moving to the right, as we go forward in time, because it's propagating out to the right like that, that's really what's going on more than anything else. The wave is shifting, and the way that it's shifting is going with essentially this minus omega t. If we wanted to watch the exact same wave, where does one peak go? Right? Where does that one single peak go? As time increases, so too does the x value. And that's what one peak looks like moving all the way across. If we don't view it like that, then it appears as if it's moving backwards at first. So keep this in mind. When it's traveling in a positive x direction, that's why we end up with this negative omega t. One other way that we can imagine this. Actually, before I do that, let me talk about this example. Let me walk through an example of one of these problems and how I would imagine going through it. Write the displacement equation for a sinusoidal wave that is traveling in the negative y direction with a wavelength. Let's write some of these things down while we're talking about them, right? Wavelength, 50 centimeters. So lambda is equal to 50 centimeters. Better yet, 0.5 meters. Speed, 4 meters per second. No changes needed for that. Amplitude, 5 centimeters. Convert that into standard units. Assume the phase constant is 0. Perfect. And then traveling in the negative y direction. So this is going to be a little bit funky. So first of all, I know that my displacement is going to look something like this. Instead of x, it's just going to be y. No other difference besides that. I know it's going to be amplitude times sine. And I know I'm going to start with a ky. But now, how do I talk about this omega t? This is going to be plus omega t. I flip the sign on the middle. But let me talk about y. Let's go back to this video one more time. And I know I'm using the crap out of this video right here. But we can see how this thing is going. And I'm trying to tell you right now, so this is moving, we can see this is moving direction positive x. And to go with that positive x, we said it's a minus omega times t. What if we played the video in reverse? What would we see then? If we took this video, when we played it in reverse, what I would see is not waves moving to the right, but waves moving to the left. That is to say, if I flipped my direction of time, I would get waves traveling in the opposite direction. So, if we're looking at our example problem here, and they tell us negative y direction, then had we put in minus omega t, we would have been stuck with the positive direction. By flipping the time, we flip the direction of the wave. It's as if it's going in the other direction. Does that make any sense? So the best description I've got of what we do with omega t is that if we look at what's going on in the video here, if this is going to the right, if this is going in the positive x direction, in the positive x direction, the equation is supposed to look like a negative omega t. If I were to reverse the video, if I were to rewind the video and play it backwards, that is to say, if I were to flip the direction of time, if I were to go in the negative t direction rather than the positive t direction, I would have also flipped the sign of my wave. I would be going in the opposite direction because of that wave. So that's my argument here, that we're going in the negative y direction. That says, okay, positive y would have been a minus omega t. But if I were to reverse the video instead, if I wanted to go in the negative y direction, then I would flip my time. So now we've got this expression, but what we've got in our given variables simply does not match. We know at the very least that the phase constant is supposed to be 0, and that does help a little bit. But now what I'm going to need to do is I'm going to need to plug in some of these things, what we just saw in the last slide. So I would start with my frequency, omega. This one's a little bit tough because I don't have anything that relates to omega here, right? I've got lambda. That's supposed to be with the wave number. So let's hold off on omega. Let's back up a second. Let's say, okay, I see lambda. I know that relates to the wave number. Wave number is equal to 2 pi divided by lambda. If I plug in 0.5 meters, then I end up with 4 pi as my wave number. Then I can say, all right, two different ways to consider this one. I can either do that, I could find the frequency, I guess, but I'm much more interested in omega. So what about this? Let me just say V is equal to omega divided by K. That is to say, omega is equal to V times K. Omega is equal to 16 pi. Now I've got K. I've got omega. We know the phase constant 0. We know the amplitude. Plug everything in. Displacement is equal to 0.05 times sine of 4 pi times y plus 16 pi t. And there we have it. So I think this gets a little bit easier the more and more we talk about some of these things. One of the things that I'm going to highlight here, I'll talk about this again one more time at the very end as a reminder, but there is a short little PHET tutorial lab done on mastering that will just allow you to kind of play around with this thing a little bit and get a sense of what's going on. I think this will very much help when we're talking about a lot of these details. How does all of this nonsense work in the first place? It makes a little bit more sense once you've got something to visualize and kind of put a stamp on. So I know some of this stuff is going to sound a little bit crazy right now. We are introducing a lot of new concepts, and that's all right. The simulation will help. Think about those details. Think about the fact that one spot, if I were to localize one spot, if I lock that down into place, and I say I'm going to look at this one particular spot, then all I see is something changing with time. And that is back to our typical harmonic oscillator. Now it's just a sine of some phase plus omega t. Perfect, right? We have seen that before. If I want to watch how something is as a whole, if I want to see what kind of shape does it actually make when I take a picture, then I say taking a picture is locking this down, saying one particular time. Now, what does it look like as it goes all the way across the wave? So we can lock down either two of these variables to get a slightly different picture of what's going on. And that's why it's a little bit harder to describe, because realistically, there are two different variables here, right? That's why we like to have these videos, because this video is taking care of not only the fact that we've got some spatial movement, but also some temporal movement, time changing. So the simulation, I think, helps with that quite a bit once you can visualize something like this just a little bit better. So one other thing that I want to kind of highlight in here, and it's not something that we're going to necessarily cover in super great detail, but you might remember when we were first introducing the simple harmonic oscillator with what feels like forever ago at this point already, we ended at something like this equation right here. And we ended here a couple different times, because we did this once with the spring and the block, then we did it with a simple pendulum, then we did it with a physical pendulum. And at the end of the day, something showed up in these parentheses right here. But what we found was that whatever was in the parentheses right there, if we took a square root of that, we had our angular frequency omega. And that was great when it was the only thing that mattered. This is when time was the only thing that we considered, right? When we're just looking at this change right there. The problem is that looking at something like a traveling wave, like d, the displacement, this has a dependency on x and t. So what we end up with in the parentheses here, we end up first with a very similar equation. Don't make that any sort of difference. This is what we call the wave equation. It's a very important equation. It's an extremely important equation. It's not one that we're going to focus on very much because it is, a multivariable differential equation. I don't expect you guys to have that mastered. However, it is extremely important in describing what's going on with my wave, and just like what we had seen from before, inside of whatever we would see in these parentheses is going to very heavily relate to whatever is going on with the speed of the wave this time, rather than just the oscillator frequency. So it's got the oscillator frequency and the wavelength both kind of tied up in there together, which makes it a little bit more unique. For light in particular, it actually comes out to be this very cool thing. If you have done any sort of electrical engineering or anything else, you might be familiar with the values, the permittivity constant and the permeability constant. They are fundamental constants for electricity and magnetism, respectively. And when you plug that in there, you take the square root of those values, and that's actually what gives you the speed of light. And that was how the speed of light was first calculated by Maxwell, James Maxwell. There's a cool thing in that one. That's something that you'll cover a little bit more in 192 than you will in this course. But that is just kind of a cool result. It's one of those things as we look at different systems, because right now we're looking at just strings and wave traveling along string. As we look at other systems, we will use a similar equation to essentially find what does our velocity look like in these different systems. It's a very similar pattern that we're going to be able to use quite a bit. So I do have one problem for you guys to try, though. Let's imagine you have this displacement vector right here. Not a vector, I guess, a displacement function, a wave function. What are frequency, wavelength, wave speed, and then displacement at this particular time and place? I'm going to say take the next 3 or 4 minutes, work on this one, see what we can come up with, and then we'll come back together and talk about what you got. Okay, so let's go ahead and start to take a look at this here. So piece by piece, the values that we've got, if I look at this thing straight on, I've got A, K, and omega right off the bat. Amplitude is 0.035 meters. Wave number, 2.7. Omega, 124. So between all of these, what I can immediately say, frequency, that's something to do with the angular frequency, right? We know the relationship that angular frequency, omega, is equal to 2 pi times f. So let's just flip it around a little bit. Omega divided by 2 pi should give our frequency back out. Frequency is equal to omega divided by 2 pi. And when we plug in that number, what we should find is something like 19.74 hertz. Same deal. Wavelength to wave number. Take the wavelength. I look at this relationship. Wave number k is equal to 2 pi divided by lambda. Flip those two around. Lambda is equal to 2 pi divided by the wave number. Didn't set up that fraction very cleanly, but that's all right. When I plug those in, I should find a wavelength something like 2.327 meters. Finally, the wave speed. We know that there's a lot of different ways that we can calculate that one out. There are 3 different expressions that could be used. And what I'm just going to do here, I'm not going to trust my rounding. Let me take the value with omega divided by k, because I'm given those values outright. When I plug those 2 values in, I find something like 45 0.92 meters per second. Finally, plug in those values. All we have to do, there's no crazy tricks with this one or anything else. I've got an x, I've got a t, I've got an expression that the only thing I need to do is plug those two in. So d, 5.2 and 3.6. Plug those numbers in directly. What we should find at the end of the day is something like, pretty small actually, 3.24 centimeters or 0.0324 for something like that. And that's my final answer for D here. How do we feel on all of that? Does the negative not affect the calculations? No, it only tells you about the direction that the wave is traveling. It tells you about the direction only. That just tells you whether it's moving to the right or to the left because it's how the wave is shifting with time. When I increase t, is it going to make the wave go this way or is it going to make the wave go this way? It is implied that the amplitude is in m. Yes. Yes. Because we're going standard units for all of these things. I mean, more technically, it should have been given in meters. But if I'm just seeing that number straight off, then I'm going to say, okay, standard units. I've got nothing else to go off on that one. Standard units are what we've got implied here. But technically speaking, units should be provided with something like this. So, one thing that I did want to highlight just a little bit, and this might be a little bit tricky. I'm going to turn down my gain a little bit, so hopefully I'm not too quiet here. But one of the things that I did want to focus on is, or not necessarily focus on, I guess, but kind of do as a little bit of an extra aside here, talking about that relationship between tension and frequency and displacement, what that actually seems to be. So let me do something like this. So on many instruments, what we end up finding is that oftentimes, so this is just a string. And the fact that it's got some boundaries here, you will see in the simulation, it changes some of the details. But my proof that displacement is not a major factor is, let me play the difference between a quiet note, a loud note, and a really loud note. And what goes on with that really loud note is that at first it has just a little bit too much displacement. And that little bit too much displacement ever so slightly does change the tension. And then it ramps back down to a regular value. It kind of falls back in line with that equation. But the impact that the increased displacement has is very minuscule as compared to what it's like to just simply change the tension. There's an ever so slight difference when I start to change the tension by pushing down at the top of my guitar right here. That increase in tension is much, 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 much more impactful than any sort of displacement variable could have, because at a certain point, what happens when you've got too much displacement? Well, you've got a broken string. So, that is kind of my demonstration of why the displacement does not make a major factor. Technically speaking, it can indeed change some of these quantities, and you would see that as a change in the frequency. The wavelength is the same because it's the same pinpoints on the outside of the guitar, but the frequency would change with the wave speed, so ever so slightly, I agree that it does change. But as compared to a realistic change in tension, no displacement is going to do that without snapping the string in the first place. So, wave speed depends on the medium, doesn't depend on the amplitude. One last thing that I've got on this one, the thing that I've already brought up before. do this in an example. See the simulation. Use that as kind of a guiding post to actually be able to see what's going on with a lot of these traveling waves. I promise this should make this whole thing significantly easier to look at and to imagine. Go through that tutorial, use that to help you. You're welcome to also play around with this FET just kind of on its own to help you visualize what's going on and all this stuff that we've talked about today. But that's all I've got, team. A little bit of a lighter day today, intended to be. It's a Friday and we're just out of an exam, so I didn't want to run you guys too hard by any means. I've already done that enough this week. But that's all I've got. Thank you guys so much for being here. I, of course, always very, very much appreciate it.